In today's video lecture, we're going to start the packet of notes dealing with capacitors and inductors. This topic is covered in chapter 6 of our textbook. Our textbook actually discusses inductors first, but we will be talking about capacitors first. Capacitors are covered in section 6.2 of the book, inductors in section 6.1, and then equivalent capacitors and inductors is covered in section 6.3. In the last portion of this packet, we will be talking about op-amp circuits involving capacitors. Our book discusses this very briefly in section 7.7, but for the most part, we're going to rely much more on our notes to cover this topic. And a very important part of this last topic is the Baxendale tone control circuit. This is a very cool circuit that you're going to see in our lab. In fact, the final project, a big portion of the final project is using the Baxendale tone control circuit. And we'll first introduce it here, and then we'll touch upon it again much later on in the semester. Anyway, before we talk about capacitors and inductors, I want to give some motivation as to why we're going to be learning about these. If you think about the progression of this course, we've been putting more and more tools in our circuit toolbox. We started with resistors. Resistors really can't do much by themselves. Basically, you can do a voltage division circuit, and that's about it. We then added potentiometers, and they added a little more interest to our circuits because it gave us a chance to manually alter the circuit. For example, you could do a volume control with a potentiometer and with some resistors. When we added the op-amp circuit element, we greatly increased the number of circuits that we could build. For example, we could add two signals together, we could subtract signals from each other, or we could even amplify a signal. But one problem with all of these circuits that we've looked at so far is that they've all been frequency independent. By that I mean that whatever the circuit is doing, it does it to all the frequencies coming into the circuit. For example, if you change the volume, it changes the volume at all frequencies. Suppose you wanted a circuit that operated differently at different frequencies. To do that, you need an element that is frequency dependent. It turns out that capacitors and inductors are frequency dependent. This means that there are lots of things you can do with capacitor and inductor circuits that you cannot do with the elements that we looked at before now. So we'll talk about this within a few lectures, but at this point let's start talking about capacitors and inductors very generally. Both capacitors and inductors, like resistors, are two-terminal devices. The big difference though is how the voltage and current are related. In a resistor, the voltage is proportional to the current. You double the current, you double the voltage, you double the voltage, you double the current, because V equals I times R. In a capacitor, we're going to see that the current is proportional to the derivative of the voltage. And in an inductor, the voltage is proportional to the derivative of the current. The fact that this VI characteristic has a derivative relationship is going to be the key to all the interesting properties with capacitors and inductors. So what are some of these interesting properties? So, in other words, why do we want to learn about or use capacitors and inductors? Well, first off, they provide memory to a circuit. In other words, you were going to find out the capacitors and inductors store some information about what was previously in the circuit. Second thing we're going to find out is both capacitors and inductors can temporarily store energy and put the energy back into the circuit at a later point. And then the big advantage, so this one gets a star, the big advantage is that they are frequency dependent. As I said before, this allows us to create a circuit that will do different things depending upon the frequency of the signal that's being applied to the circuit. So let's talk about capacitors first. Before we talk about capacitors as devices, let's talk about capacitance as a phenomenon. So imagine you have two different conducting bodies. So one body up here and another body down here. Let's assume there's a whole bunch of excess positive charges on this conducting body and a bunch of excess negative charges on this conducting body. What that's going to create is an electric field or an E field pointing from the conducting body with excess positive charges to the body with excess negative charges. This in turn is going to cause a voltage difference between the two bodies. So you have a plus there and a minus there with some voltage. It turns out that this is what we call capacitance, this phenomenon that if you have two conducting bodies with opposite charges on them, it creates a voltage across this. This is what we call capacitance. And there's a ratio between the charge on the bodies and the voltage between them, and that is a constant, and that is what capacitance is. Specifically, capacitance is charge per unit volt. You can think about capacitance as capacity to hold charge. So what are the units of capacitance? Well, the unit of capacitance is a farad, which we abbreviate with a capital F. And if capacitance is charge over voltage, the units of charge is an ampere second, and the unit of voltage is a volt. So 1 farad is 1 ampere second per volt. A good analogy of capacitance, and we'll talk about analogies a little bit on the next page, is how much water can you hold in a water balloon for a given water pressure. So let's talk about the capacitor now as an electric device. So a capacitor consists of two metal plates separated by some non-conducting or dielectric material. So you might have a metal plate up here, another metal plate on the bottom, and then in between it you might have air or some other non-conducting material. What happens now, suppose you apply a voltage across the capacitor. So let's say a battery. What that's going to do is this battery is going to start pushing current out its plus terminal, and these positive charges are going to land on this positive plate. They can't go any further though because of this non-conducting material. But what those positive charges on the one plate are going to do are going to push the positive charges off the other plate, in other words, causing current to continue to flow through here and putting negative charges on the bottom plate. Now, technically, the opposite happens. Technically, remember, it is electrons that are moving. So technically, it is electrons coming from the negative terminal of the battery, landing on the bottom plate, and pushing electrons off the positive plate. But since we try to think of current as the net motion of positive charge, we think about the positive charges being placed on the top plate and being pushed off the bottom plate, although once again, in actuality, it is the other way around. The schematic symbol for a capacitor is going to be two plates, two lines. Sometimes they are parallel like this, and sometimes one of them is curved. When one of the plates is curved, that's always the negative plate. We actually give these two plates different terms. The positive plate we call the anode, and the negative plate we call the cathode. In general, current always enters the anode of a device. So the current or the positive charges enter the anode, or another way of thinking about that is the electrons always leave the anode. Okay, so this is what happens. So if you take a capacitor, we apply a voltage across it, as I said here, and that causes a flow of current. The charges have nowhere to go, so they congregate on the positive plate. They accumulate on the positive plate, which causes negative charges to accumulate on the lower plate. Those charges then create a voltage. That voltage counteracts the voltage being applied and slows the current. Eventually, when the voltage drop across the capacitor is equal to the applied voltage, the current stops and the charge accumulation is complete. And what happens now is the capacitor just sits there holding these positive charges on one plate, the anode, and negative charges on the cathode. So a couple analogies. One analogy that I like is a water tower. Imagine now a water tower with a pump. The pump you can think of as the voltage source. The water tower you can think of as the capacitor. So the water pump is going to push water up into the water tower. As it pushes water into the water tower starts building back pressure, making it harder for the pump to continue to push water up there. Eventually, when the water tower is full, the back pressure from the water in the tower matches the pressure of the pump and the water tower is full. Another analogy, as I mentioned on the previous page, is a water balloon. Same type of idea here. Imagine a balloon being connected up to a hose. When the balloon is empty, it's pretty easy for the water to fill into the balloon. As a balloon fills up, it creates a back pressure that counters the pressure coming from the hose. If you don't increase the pressure from the hose, eventually the water balloon will get to a certain size and it'll stop, because the back pressure from the water balloon equals the pressure from the hose itself. And we say the water balloon is filled up then. So we'll revisit these analogies later on as we continue to talk about capacitors. But at this point, what you need to remember is that when you have an applied voltage, it puts charges on the capacitor plates, positive charges on one plate, negative charges on the other plate. It does it until the capacitor is at full capacity, when it holds all the charge that it can for that given voltage, and then it just holds those charges. What happens then is at a later time, which we'll talk about later on, they can release this charge to the circuit. In other words, it can be releasing energy to the circuit. Okay, let's look at some equations now related to the capacitor. We saw before the capacitance is charge per unit volt. If you rearrange that equation, you get the charge is equal to capacitance times the voltage. If you now take the derivative of both sides, the derivative of charge dq dt is current. So current into a capacitor is the derivative of the capacitance times the voltage. Since the capacitance is just a constant, we get that the current is the capacitance times the derivative of the voltage. And this is what we talked about earlier. The current through the capacitor is proportional to the derivative of the voltage. Very, very different than with resistors, where the current is proportional to the voltage itself. We can take this IV relationship and express it in integral form by saying the voltage is the integral of the current. Just like other situations earlier this semester, whenever you had an integral relationship between two different measurements, it was a definite integral. So that means that the voltage at any time, t, is a voltage at some beginning time t naught, plus 1 over c times a definite integral from t naught to t of IC tau d tau. And the reason we use these taus, it's a dummy variable. And we'll see that in an example that we'll get to very shortly. Two more important points before we continue on. One is this term here. The fact that the voltage across the capacitor at a given time is a function of the voltage across the capacitor at a previous time means that there's going to be history involved, or that this capacitor has some memory to it. This is going to be an important point, as we're going to see. Another important point we see is that if you look at this equation here, because the current is proportional to the derivative of the voltage cannot change instantaneously. If the voltage changed instantaneously, the current would be infinite, which you cannot have. So the way we mathematically say that a voltage cannot change instantaneously is by this term down here. We say that the voltage across the capacitor at time t naught minus, that's what this little minus means. What this means is the time, the instant right before time t naught. The voltage across the capacitor at time t naught minus is equal to the voltage across the capacitor at t naught plus, which is the instant right after time t naught. Basically what this means is that if you plotted the voltage across the capacitor versus time, you cannot have a situation like this. You cannot have the voltage going like this and then have a sudden jump. This is not allowed, because this is called an instantaneous change in the voltage across the capacitor. The derivative of that would be infinite, or in this case negative infinite, which would give you infinite current, which you cannot have. Let's do a simple example. Let's say that we have a 1 millifarad capacitor, and let's say that the voltage across it is a triangle wave. So this is the voltage across the capacitor. and we want to find an expression for the current through the capacitor. To solve this problem, the first thing you want to do is come up with an equation for these two line segments. You have a line segment here for this part of the triangle wave, and then you have this part of the triangle wave. What you want to do probably is the slope-intercept form. So if you look at the yellow part, you'll see that its slope is 2, and the y-intercept is 0. So VC of t here is just 2t. For this line segment, you sort of have to extrapolate where this line segment would have the y-intercept. It would have the y-intercept, about 40, actually exactly 40. And so VC of t for this line segment is going to be minus 2t plus 40. Minus 2t because the slope is minus 2. Okay, so now we have an expression for VC of t for the two line segments. So now we can solve for IC of t. IC of t, as we remember, is C, which is 1 millifarad, times VC of t dt. Since we have two distinct slopes here, we're going to have two distinct regions for the current. For time between 0 and 10 seconds, that's going to be this stuff to the left of this line here. The slope is 2, so IC of t is going to be 2 times the capacitance, which is 0.001 farads, and so we get 2 milliamps. For time between 10 and 20 seconds, that's this part here. Once again, IC of t is the slope, which is negative 2 times the capacitance times 0.001, or minus 2 milliamps. So if we were to plot the current versus time, you would see that it would be 2 milliamps up to 10 seconds, and then immediately at 10 seconds, it would jump to negative 2 milliamps. One thing to note here, you can have a discontinuity in a current. That is the discontinuity. From the previous page, we said that the voltage cannot change instantaneously. We said nothing about the current. Let's go the other way now. Let's assume we have a 1 millifarad capacitor again. Now let's say that we have the current as a triangle wave and we want to find the voltage across it. So once again, to solve this problem, we first need to break up this problem into its two distinct parts. So between 0 and 2 seconds, we have this slope line going up. Between 2 and 4 seconds, we have the slope line going down. So the first thing we want to do is come up with an equation for each of these line segments. So this first line segment, using the slope-intercept form, I of t is the slope, which is 0.1, and the y-intercept is 0. So I of t is just 0.1 t. For this second line segment, you'd have to extrapolate it over here to get the y-intercept. The y-intercept would be at 0.4 amps. So this line segment, I of t, is going to be minus 0.1 t plus 0.4. And I guess these are both amps. Once again, why is it negative 0.1? Because that is the slope. Now that we have expressions for the current, we can now find the expression for the voltage. Remembering that the voltage across the capacitor is the initial voltage at some starting time, which we're going to call 0, plus 1 over C. So once again, going back to this equation here and this page here. So VC of t is VC at time t0, which in this case is 0, plus 1 over C times the integral to 0 to t of IC tau d tau. So VC of t is going to be VC of 0 plus 1 over c times the integral from t0, which is 0, to t of, in this case, that expression there. And I'm going to use my dummy variable tau, and you're going to see why in a minute. 0.1 tau d tau. So if you work out this math, VC of 0 is 0. We're told that. So VC of t is going to be 1,000 times the integral of 0.1 tau. The integral of 0.1 tau is 0.1 tau squared over 2. And we're going to evaluate that at the lower limit and the upper limit. So you get 1,000 times 0.1 tau squared over 2, replacing tau by t. So you get 0.1 t squared over 2. And you subtract from that the value of the thing in brackets evaluated at 0. 0 squared is 0. So you get that. And you work it all out, you get 50 t squared volts. This thing was valid for t between 0 and 2 seconds. For t between 2 and 4 seconds, we have a slightly different equation. VC of t is now VC at time 2, this is our new starting point, plus 1 over cap c, 1 over the capacitance, times the integral from 2 to t of negative 0.1 tau plus 0.4 d tau. The voltage across the capacitor at 2 seconds, you work it out, is 200. Where does that 200 come from? 50 times 2 squared plus 1,000 times the integral of minus 0.1 tau plus 4. The integral of minus 0.1 tau is minus 0.1 tau squared over 2. The integral of 0.4 is 0.4 tau. And we're going to evaluate that expression at the upper limit of t and the lower limit of 2. So you work out the math, it's 200 plus 1,000 times, plugging in t, you get 0.4 t minus 0.05 t squared. Then we're going to subtract 1,000 times the expression in the brackets evaluated at 2. 0.4 times 2 is 0.8 minus 0.1, 2 squared over 2. You work out all that math, you get minus 50 t squared plus 400 t minus 400 volts. We could then draw this if I had space. I guess I will draw it over here. Don't have a lot of space here, but I'll try to draw this. VC of t. 50t squared is going to be a parabola. It's going to look like this. And that's going to be valid between t of 0 and 2. And at 2, we saw that this evaluates to 200. So that is that. Between 2 and 4 seconds, this is our voltage. If we were to plot that, it would look like that. And it actually maxes out at 400 volts. It's 400 volts at 4 seconds. So this parabola gives us that. What we notice is this voltage is continuous. Notice there are no jumps. Current can have a jump or a discontinuity. Voltage cannot have a jump or discontinuity. The next thing we're going to talk about briefly is the capacitor in DC steady state. So let's assume we have a voltage source, Vs, and it's pumping charges onto the plates of the capacitor. Positive charges on the top plate or the anode, negative charges onto the bottom plate or the cathode. Eventually, what's going to happen as you get more and more charges, the voltage across the capacitor, Vc of t, rises. Eventually, Vc of t equals Vs. And that is when we get what we call DC steady state. In DC steady state, if the voltage across the capacitor is a constant, its derivative is zero. If its derivative is zero, the current is going to be zero, and the capacitor stops charging. In this situation, what we call DC steady state, we can model the capacitor as an open circuit. And the charge that's on the plate of the capacitor, we know from the equation relating the charge, the voltage, and the capacitance. We see that the charge across the capacitor when it's in DC steady state is the capacitance times the voltage across the capacitor. So here we have a 16-volt source, and it's connected through a couple resistors to a 0.25 microfarad capacitor. At time 0, we're going to flip the switch, and this of course is going to allow current to flow through the 1 kilo ohm resistor. Some of it's going to go through this 3 kilo ohm resistor, some of it's going to go into the capacitor and start depositing positive charges on the top plate, negative charges on the bottom plate. The voltage across the capacitor is going to increase. Eventually it's going to stop. When it stops, the capacitor looks like an open circuit, and we have DC steady state. But is the voltage across the capacitor going to be 16 volts like it was on the previous page? Well, let's look at it. In DC steady state, you model the capacitor as an open circuit. We have 16 volts. You have a 1 kilo ohm resistor here. We have a 3 kilo ohm resistor here. The capacitor in steady state gets modeled as an open circuit. And here we have voltage division. Vc in DC steady state. We have a voltage division situation. The voltage across the capacitor is going to be 3 over 3 plus 1 times 16 volts. So Vc is 3 over 3 plus 1 times 16 volts, or 12 volts. So notice that the steady state voltage across the capacitor is not necessarily equal to the voltage being applied. It depends upon what other resistors you might have in the circuit. That actually was not the question. The question was not what's the DC steady state voltage. The question is how much charge will be stored on the capacitor after a long time after the switch is thrown, or once we're in DC steady state. Well, we know that the charge on the two plates of the capacitor is equal to the capacitance times the voltage. So you have 0.25 microfarad times 12 volts, or 3 microcoulombs. Technically, it's plus and minus 3 microcoulombs. You have plus 3 microcoulombs on that plate and negative 3 microcoulombs on that plate. What we're going to see later is we're going to see how the voltage gets to the DC steady state. It doesn't get to this 12 volts instantaneously. How it gets there is what we call transient response. That is going to be in the next set of notes. Another random topic about capacitors is what we call AC steady state. And this is where the frequency dependency of the capacitor really starts being seen. So we're going to see the frequency dependency of capacitors. AC steady state is a topic we're not going to look at for a few more weeks, but basically it means when you have a sinusoidal input being applied to a circuit for a long time. Just like DC steady state means you have a DC signal being applied for a long time. So let's assume that the voltage applied across the capacitor is a sinusoid with an amplitude of Vc and a frequency of omega and a phase of phi. We're not going to really worry about the phase too much at this point. So the current through the capacitor, or the current into the capacitor, is the capacitance times the derivative of the voltage. The derivative of cosine is negative sine. So we get negative sine. Furthermore, this omega that's inside the cosine comes out as part of the derivative. A couple of trig identities are important here. One, sine of x is the cosine of x minus 90 degrees. Also, minus sine of x is equal to cosine of x plus 180 degrees. So if you combine these together, so if you look at this expression here, you have a sine, which is going to add a negative 90 degrees to the angle, but we also have this minus sign, and this minus sign is going to add 180 degrees. So putting those together, we see that IC of t is omega c VC times cosine omega t plus phi plus 90 degrees. So there are two things we see from this. First thing is we see that the angle of the current is 90 degrees more than the angle of the voltage. So the angle of the current is phi plus 90 degrees. The angle of the voltage signal is phi degrees. We say that IC leads VC by 90 degrees. Sure enough, if you were to plot this over here on the right, the current is this expression here. The voltage is this waveform here. We see that the current peaks earlier than the voltage by a quarter period. Quarter period, or 90 degrees. And so that's what we mean by the current leading the voltage by 90 degrees. That in itself is not all that interesting. What's more interesting is the second aspect of the relationship between the voltage and the current. Notice that the voltage magnitude is VC. Regardless of your frequency omega, the voltage is VC. The current magnitude, though, is omega times C times VC, which means the amplitude of the current depends upon the frequency of the voltage. The amplitude of the current depends, among other things, on the frequency of the voltage. What that means is if you took a ratio of voltage magnitude to current magnitude, you would get voltage magnitude over current magnitude. Voltage magnitude is VC. Current magnitude is omega times C times VC. These cancel, and you get 1 over omega C. If you think about what voltage over current means, think about with the resistor, V over I is a resistance. So what this is telling us with the capacitor is its resistance, and I'm going to put resistance in quotes because it's not really a resistance. Its resistance is frequency dependent. As the frequency goes up, this ratio of voltage to current goes down. So we have that the capacitor is a frequency dependent resistor. And I'm using these quotes once again because it's not really a resistance. In fact, the proper term, we're going to talk about this later, is we use the term impedance instead of resistance here. But we will talk about this much later. At this point, what's important on this slide is to understand that the amplitude of the current is a function of the frequency of the voltage. That doesn't happen in a resistor. In a resistor, if you take a sinusoidal input voltage and apply it to a resistor and measure the current, if you increase the frequency of the voltage signal, the frequency of the current will increase, but the amplitude will not increase. Here, however, we see that if you take a capacitor now and apply an AC, a time varying voltage across that, as you increase the frequency of the voltage, the magnitude or the amplitude of the current increases. This is the frequency dependency that is a property, and a very important property, of capacitors. Another important point with capacitors that is based upon this frequency dependency is the use of capacitors in circuits. We use capacitors as both coupling capacitors and bypass capacitors. This one you've seen already. Bypass capacitors you've seen in lab. Specifically, you saw them with op amps. But let's talk about coupling capacitors first. Basically, a capacitor, because it is a DC open circuit, it does not let a constant voltage pass if it's been sitting there a long time. You can put a capacitor between different stages in a circuit to block DC voltages, but at the same time allowing time varying or AC voltages to pass through. And once again, this is based upon the fact that for DC signals, a capacitor is an open signal. So in this diagram down below, this is a coupling capacitor. For example, if the input is 5 plus 2 cosine of 100t, this capacitor here is going to block the 5, and so you're going to have no DC component. At the output of the capacitor, and that is because of this coupling capacitor right there. The other use of capacitors in a circuit often is what's called a bypass capacitor. These are capacitors that you place between the power supplies connected to the op amp and ground. So the bypass capacitors would be this capacitor there and this capacitor there. Basically, what these are, you can think of them as shock absorbers. The power supply, let's say the VCC, a typical power supply, let's say it's a 15-volt power supply. It's not necessarily going to be exactly 15 volts. It's going to have a little ripple to it. What happens now, remember, the capacitor is a DC open circuit, but for higher frequencies, a capacitor acts like a short circuit. What this means is that the variations, the ripples, the high frequency ripples, are shorted to ground. So the high frequency ripples have a path through the capacitor to ground. The DC component, the part we want to keep from the power supply, gets fed directly to the op amp. So just like a shock absorber on your car keeps the small bumps in a road from making its way to the passenger compartment of the car, the bypass capacitor keeps these high frequency ripples from the power supply from getting into the op amp by going to ground instead. The next thing we're going to talk about briefly is energy storage in a capacitor. At the beginning of this lecture, I mentioned that capacitors and inductors both store energy temporarily. A capacitor stores energy in its electric field. Remember, we mentioned that there's an electric field between the positive and negative plates of the capacitor. That is where this energy is going to be stored. How do you calculate what this energy is? Well, energy is always the integral of power, and this is a definite integral. So it's the energy at some time t naught plus the integral from t naught to t of p tau d tau. Power, of course, you could write as voltage times current, but current into a capacitor is C times dVc dt, and then you get from there, you get the expression below. I wouldn't worry so much about these three lines here. What's important is the final expression. The energy stored in a capacitor at any time is equal to 1/2 times the capacitor value times the voltage across the capacitor squared. Note that this is never negative. Whenever you have charges stored on a capacitor, You're going to have a voltage across the capacitor due to the capacitive effect. Remember, charges on two conducting plates create an E field, create a voltage difference between those two plates, and that voltage there gives rise to this energy that's being stored. Later on in this semester, we'll see how this energy can be used to drive a circuit once the capacitor loses its energy. Just like if you have a water balloon, once you release the water balloon and let that water gush out, that energy that's stored as potential energy in the water balloon gets released. Just like you have a water tower where you have water in the water tower. Once you let the water out of the water tower, that potential energy stored in the water tower gets converted to kinetic energy. Let's look at an example relating, once again, current to voltage to power to energy. So in this example, we have a current source passing through a 1 ohm resistor to a 2 farad capacitor. These are not very realistic numbers here, but it makes the math simple. Let's assume that the current is a constant 8 amps going in this direction, which is going to cause positive charges to accumulate on that plate and negative charges to accumulate on that plate. Then, after 1 second, we're going to reverse direction. And now we're going to start pumping positive charges onto this plate, which is going to cause negative charges there. So let's first off see what the voltage is going to be. And as before, we have two distinct times of operation between 0 and 1 second and 1 and 2 seconds. So for time between 0 and 1 second, we know the voltage across the capacitor is equal to the voltage at time 0, which was 0, plus 1 over c, which is 1/2, times the integral from 0 to t of IC of tau d tau. But IC is just a constant between 0 and 1 second. So it's going to be 8 d tau. The integral of 8 d tau is 8 tau. So you get 1/2 times 8 tau evaluated at an upper limit of t, a lower limit of 0, which is just 4t volts. Sure enough, that is this line segment right there. For time between 1 and 2 seconds, Vc of t is equal to the voltage across the capacitor at time 1 plus the integral from 1 to t of -8 d tau. The voltage across the capacitor at time 1 is 4 volts. Whoops, I missed one thing here. We need the 1/2 because remember it's 1 over c. So we forgot that 1/2, put that there. So we get 4 volts plus 1/2. The integral of -8 is -8 tau. We want to evaluate that at the upper limit of t and the lower limit of 1. So we get 4 plus 1/2. The thing in brackets evaluated at the upper limit is -8t. Then you subtract its value at the lower limit. -8 tau, when tau is equal to 1, is -8. We're subtracting that. You got to be careful about that. You have double negatives there. And when you work out all the math, you get 8 minus 4t volts. Turns out that is what that line segment is. So you can sort of visualize it a little bit too if you look at this current and think about integrating it. As you integrate the area under here, it should increase linearly up to a point. And then at time 1 second, we're going to start decreasing at the same rate. And so the rate it goes up is the same as the rate it comes down. And notice by the time you get to 2 seconds, the positive area, the area in blue, equals the negative area, the area in red. And so the voltage is going to be 0 again. So another way to think of it, looking back at the circuit, is between 0 and 1 second, we're pumping positive charges onto the top plate, Between 1 and 2 seconds, at the same rate, we're pumping positive charges onto the bottom plate, sort of undoing what we did in the first second. Continuing on with the power and the energy now. So power, PC, just the voltage across the capacitor times the current through the capacitor. So point by point, you multiply the current times the voltage. So between 0 and 1 second, 4t gets multiplied by 8. That's going to be 32t. Between 1 and 2 seconds, we get negative 8 multiplied by 8 minus 4t. You get 32t minus 64. And so the power looks like that. How about the energy? The energy stored by the capacitor is the integral of the power. Remember, integral is nothing more than an area. So the energy starts at 0. It increases slowly at first, but then more and more quickly. So it's probably going to be a parabola shape. Then it's going to start decreasing very quickly at first. Then it's going to slow down. And by the time you get to 2 seconds, the negative area equals the positive area. So it's going to go down like that. To find an expression for that segment and that segment, you can use the fact that the energy stored in a capacitor is equal to 1/2 C times Vc squared. Now in this problem, I purposely chose the capacitor to be 2 to make this math really, really simple. That cancels with the 1/2. And so the energy stored in the capacitor is just the voltage squared. 4t squared is 16t squared. 8 minus 4t squared is that segment there. And that is the equation now for the power. You get the power here. You get the energy here. You get the voltage here. All of those we get just knowing what the current is. So this example actually showed a lot of different things at once. It showed the relationship between current and voltage. It showed the relationship between current, voltage, and power. Finally, it showed the relationship between power and energy, and then verified that it also gives us this relationship between energy and voltage. A couple more things to point out here. First off, notice that the voltage does not change instantaneously. You can have a corner, that's okay. A corner there, a corner there, a corner there. That's allowed, but you cannot have a discontinuity. You cannot have discontinuity in voltages. You can have discontinuity in currents. You can have discontinuity in powers, but you cannot have discontinuity in voltages. Second point I want to point out is notice that the energy is positive. The energy stored in the capacitor is never negative. And that's because the energy stored in the capacitor is 1/2 C times Vc squared. So whether the top plate is at a higher voltage or the bottom plate is at a higher voltage, when you square it, it's going to be positive. We have one more slide in this lecture about capacitors, and that is dealing with reading capacitors. So you're very familiar with reading resistors, and you know that you have the different color bands, and you have the mnemonics for remembering what different colors are. Capacitors in many ways are actually easier to read. So for larger capacitors and a lot of electrolytic capacitors, I'll fall into this category. They're capacitors that look sort of like cylinders. The value of the capacitor is written right on the capacitor. Pretty darn easy to figure out. It's 22 microfarad. One other thing that a lot of capacitors have is a voltage. This is called a maximum voltage rating. This is basically the highest voltage that they guarantee that that capacitor can be connected to without the capacitor exploding or burning up or failing. Another analogy is, think about a water balloon that you're going to be connecting up to a hose. There might be, if you have too much pressure in the hose, it could just burst the water balloon. That same thing with capacitors. If you have too much voltage, it tries to pump too much charge onto the capacitor. It cannot hold it. The capacitor fails, often burning up, popping, or other nasty things like that. One more point on this first example here is you'll notice these two leads, one of them is longer than the other one. Whenever you have a capacitor with leads that are different lengths, the longer capacitor is the positive end, and once again we call that the anode. The shorter one is the negative end, or the cathode. Capacitors that have a positive and negative end like this will always be drawn on a circuit diagram, as I mentioned before, with this symbol here, with once again the positive end being the one that is straight and the negative end being the one that is curved. We call these polarized capacitors. Polarized capacitors, it is important to make sure to connect the positive end to the right place and the negative end to the right place. The other way that you read capacitors is smaller capacitors, and a lot of the ceramic capacitors or disc capacitors that we use in lab are of this type. They use a numeric code. The capacitor value in picofarads, and pico once again is 10 to the minus 12, is written as two significant digits plus a possible multiplier. So you're going to see three numbers on these capacitors. The first two are significant digits. The third one is a number of zeros to add, and that tells you how many picofarads the capacitor is. So if you look at this one, it's 104 is a number on there. What does that mean? The first two are significant digits, 1, 0, and then the 4 means you add 4 zeros, and that is picofarad. So it's 100,000 picofarads, or 100,000 times 10 to the minus 12, which is the same as 0.1 microfarad. Let's look at one more example here. So this one has the number 475. It's a little tough to read in the picture, but 475. First two numbers are significant digits. Then 5 zeros, 1, 2, 3, 4, 5. And once again, that is measured in picofarad. That's 4,700,000 picofarads, which is the same as 4.7 microfarads. Two more things that are on this particular capacitor. Once again, it has the voltage rating, just like this one did. And the second thing that it has, notice a little J here. These letters give you tolerance. So resistors, if you remember, have a gold band or a silver band to let you know what tolerance it has. Capacitors have a letter. So this J means that it's 5% tolerance. This wraps up this lecture. Next class, we will continue on with this packet and we will talk about the inductor. What we're going to see is a lot of these properties with capacitors. We have very, very similar but opposite properties with inductors. And we're going to see that throughout. Just like a capacitor, the current is proportional to the derivative of the voltage. In an inductor, we're going to see the exact opposite. The voltage is proportional to the derivative of the current. And we're going to see that throughout the properties with the inductor. We're going to see they mirror capacitors very, very well, but everything is opposite. So we will pick that up at next class. Goodbye.